Hey, welcome to What the Fudge. I'm going to be going over today talking about how different molecules can actually mix, how that actually occurs. Okay, so only two. I'm only focusing on two today. I might show a bit more, but two. So this is chemistry, right? So when you have, we're going to call it molecule, and the one part of it we're going to call A. A is apparently not working. A is the polar. Where is this? Polar. So it's an end that's polar, or should I just say charged? Yeah. No, we're not necessarily a full charge, but like at least a partial charge. Okay. At least some sort of charge here, to where it's not just a neutral molecule. And then we have B, and this is going to be non-polar or neutral. Okay. I don't like having these big spaces here, so I'm going to get rid of those. Okay, so that's what we're going to call them. Okay, so in a molecule, sometimes you have molecules that are just A. Sometimes you have molecules, and this, not always, you can have large molecules that are polar the whole way, but often small molecules. And then you can have non-polar, which often you can have large molecules as well that are like that. And then you have sometimes, it has to be a somewhat larger molecule, somewhat, it doesn't have to be very big, but somewhat larger. Because if it's too close, let's say you have a non-polar molecule, let's say you have a carbon, right? Like this, you have a ketone at this end, right? It's polar, but like there's not that much space between the polar part and the non-polar part. Okay, so realistically, this molecule, you could have drawn one less carbon, for the most part will act like a polar molecule because of that. Especially if you have if you were to show the polar, right, obviously electrons get drawn towards here. Okay, so yeah, so usually when you have both, it's a slightly larger molecule. So then, how do things mix? So let's say we have water, for instance, okay? You have the deformed cup, you have water, and here, blue. And you have a cup of water. So what's happening with water? Well, water is an example of a molecule that's, oh no, it's blue. That's A. Water is just A. It's a polar molecule, right? So that's A. And then when we draw water, it looks like H, O, H, right? And then this means partial, negative. And the reason why you're getting this is because the oxygen, right, loves to, these are lone pairs, loves to pull the electrons from hydrogen. So there's enough interaction between the oxygen and hydrogen to where the oxygen and hydrogen stay close together, right? They stay interacting, but the electrons are really more towards oxygen than they are towards hydrogen, because oxygen likes having the electrons to it more than hydrogen does. Okay. Well, that's your water, right? So this is polar clearly, okay? Because one side negative, one side partial negative, one side partial positive. Okay, so it's clearly there's you call it well, it's asymmetrical in terms of where the electrons are going in the molecule, like where you have the partial negative and partial positive. But yeah, there's a difference. You can see a clear difference. Here it's positive, here it's negative. So this is polar, right? And so you can clearly see if they had something else that was partially positive, right? Something else that's partially positive, or something that was fully positive, that was actually charged, like full charge, right? Full charge. Then it would interact very well with this, because positive, negative likes positive, positive likes negative. You see that here, right? Now positive goes to negative, and then you'd get really good interaction between this molecule and something else that has a positive and interacts well with the negative, right? And vice versa, if you had something else here that was negative, it would interact well with this hydrogen, right? It would have a good interaction as well. Even though it's not the same molecule, you'd end up with, these are to show like an interaction, but not an actual, we call it a bond. When there's enough interaction between things, it becomes a bond. So a bond is just, let's say you have oxygen and you have hydrogen, right? When there's enough interaction such that this atom right here is, interacts enough, is strongly enough interacting with this, then we call that a bond. Okay, that's what that is. That's what a bond is. But you can still have interactions with things, and because it's a bond, we could say it's part of the same molecule, right? So we identify it as its own molecule. This is no longer just oxygen. I mean, oxygen by itself is pretty rare, but for example, this isn't no longer just oxygen and just hydrogen, right? And those atoms are still there, but now we can say that they're a molecule together, right? And obviously, I'm only looking at one side of water right now, but that's what's occurring, okay? There's enough strong interaction to where you end up with, we call it a bond. When there's a strong enough interaction such that it forms a new molecule, that's what we call a bond. You can also have other interactions that aren't as strong, okay? So you could have, let's say, between water molecules, right? So we're going to draw this again. Between water molecules, oxygen, hydrogen. Right, I'm not going to draw the partial charges again, but you know that the electrons like to go to oxygen, okay? And then I'm going to draw lone pairs. I could show why this works, why this is a stable molecule in terms of electrons going around the protons, to where the oxygen isn't going to try to get more protons, but it can form another interaction with another molecule. If you remember from the last video, if that's what the universe wants. If that makes the system stable, right? Then this is stable. But sometimes, I was hoping to not talk about this until a later video, but sometimes you end up with something where it's actually more stable if it does something else. And that's because you can have something that's as stable, we'll say, as stable as it can get within this system. And if it's as stable as it can get within this system, this is system 1, okay? If it's as stable as it can get within system 1, that's what will happen. But let's say then you were to mix system 1 and you were to put it with into another thing here, that's system 2. So system 2 already is as most stable as possible, and system 1 is as most stable as possible. If you put them together, then you would get something else, right? It would reach something else. And in terms of stability, it might actually be even more stable than system 1 or system 2, such that if you were to add other stuff to it, right? If you were to mix it with another system, let's call it system 4. I was hoping to not talk about this till later, but it's okay. If you were to mix it with another system, system 4, right? There would actually be nothing happening. There'd be no change within the molecules here, because it's already as stable. It's approaching as stable as it can get. It's more stable than what would happen if you mix system 4 or system 3. So it doesn't want to do it. But you can, in your system 1 is as stable as possible, but it could be more stable. It's just as stable as it's possible within this little system. Okay? And then when you take it, you put it into a larger system, in a larger system, then this isn't actually the most stable anymore. There's something else that's the most stable, and then it'll do that. Okay, so that's what I need by more stable, but this is already stable. So by that logic, what it means is that water is a stable molecule by itself, right? It exists, right? And we know it exists. We've clearly seen that water exists, right? We know water exists. Scientists have identified that water is oxygen to hydrogen. So water is stable, right? And I mean, there's some molecules that humans make that don't last very long. Some molecules that last less than a second that humans actually make, but it's pure. It's not really. We don't use it for anything. It's just to see if we can actually make them. There's some molecules that we do that just for science. We just see if we can make them, very large molecules. But they don't last very long. But this does last, right? So it's stable. But if you were to put this with something else, right? You could, if you put it with another molecule, those molecules could react to make something else, right? And if it reacts just automatically when you put it with something else, right? Then we say that that new molecule should be more stable for that to happen. Okay? I can get into that in reactions later, but this is stable by itself, but in some cases it can be more stable. Yeah. And one way that water makes itself more stable, so we're not doing a reaction right now, we're just doing interactions between molecules. One way that water can make itself more stable is, remember I said earlier, if you have negative and you can connect to a positive, negative connect to a positive. Well, I'm going to draw it here again right now. Negative, partial positive. Positive. Okay, so what happens is water I said negative to positive. When you have water, you don't just have one molecule of water, right? If you have a cup of water, there's lots of molecules of water. There's a lot of them together, right? There's a lot of them together. So what happens is that you actually get interactions between the molecules. So we're gonna draw interaction of the molecules. Remember, the strength into the interaction is what dictates what kind of, if it's a bond. If we say it's a bond, we define a bond as if it's a strong enough interaction versus interaction, but it's not enough to actually make it a new molecule, right? You can separate the two molecules afterwards, right? So it's not strong enough to be part of the molecule, but it's strong enough to where they interact and they stay close together. Okay? So here, what would happen is, actually that's wrong. What would happen is you'd get another proton. Okay, so you can see the structure forming. And because you have this structure, there's so much interaction between the water molecules. Water is a very strong substance. It really likes to stay together, and this interaction between water molecules, this is called hydrogen bonding. And the reason why they separate this from other types of bonding, which would just be like, you can also have positive to negative. You can have that existing, not with hydrogen as the positive and not with oxygen as the negative, but with something else. You can have something else, and you can have an interaction because you have the positive negative. But because the partial positive and partial negative of oxygen and hydrogen is so strong, it's such a strong thing, they give it a special name. They call it hydrogen bonding. And it's also important because water is such a strong thing that we felt that we had to give the interaction between water molecules a special name. So we gave that as hydrogen bonding. If you saw my last video, you might have noticed, remember the diagram I drew, which I can draw right here. So, I don't know, that was odd. So we have the diagram of last video, right? For water, right? If you haven't seen the last video, I mean, that's okay. I mean, you don't really need it. I kind of explain it here, but I would go see last video. I mean, I think it's important. Pressure, temperature, and this is wrong. I'm not going to write the units, but you should write the units. So kPa in degrees Celsius. So for water, right? I'm not going to go over the whole diagram again, but you might notice here this is solid, right? And this is liquid. You might notice, very odd, and this doesn't happen for other molecules, okay? That when you actually, what you would think with pressure, I haven't really talked much about what pressure does, but with pressure, right, what it does is that it compacts the molecules. Because the molecules, depending on the pressure, right, they'll spread out to whatever the universe wants, right, whatever the universe wants. For it to be stable, and you might need, what do you mean stable? What do you mean stable? There's no reaction going on. I mean stable in terms of interactions, right, there's the interactions going on, right? That's what I mean. So there's a certain distance at which these interactions make the system, whatever system it's in, the most stable. Okay, and that can be, well, in this case, right, it likes the interactions with water. But depending on what's there, right, sometimes you'll have favorable interactions, but if they get too close, then they don't like being too close. Or if they're too far, they don't like being too far because they want to interact somewhere. Depends on the molecules. So then you'll get sort of an ideal distance of interaction between the molecules. Okay? But this ideal distance will change depending if you have pressure, because that'll press things together. Okay? So they might want to spread out a bit. Right? They might not want to be that close, but they have to be that close, because they're literally being, with a force, being pressed. Okay? That's what you see here. But water is an odd one, okay? Because of these interactions are so strong, right? When you actually, for most things, when you press in, it becomes more of a solid if you keep pressing and pressing and pressing and pressing. And then if you let go, right, it spreads out, becomes a liquid. If you let it spread out enough. That's for most things, okay? You can see that you can't see that here actually, but for most things, when you have the same temperature but you increase the pressure, it moves to become a liquid. I mean, it moves to become a solid. Okay? Water is kind of odd. You can see this actually goes backwards. That means that when you increase the pressure, at the same temperature, if you're at 0, right? Or not 0. Let's say if you're at here, right? You're here. Normally when you increase the pressure, things become a solid, right? So normally, if I was here, if I increased the pressure, there should be a line coming like this, okay? And that means that if you increase the pressure enough, it becomes a solid. But that's not what water does. Because of this bonding, this hydrogen bonding, what actually happens is that when you increase the pressure, right, you actually end up with water becoming a liquid. And it's because, yeah, it's weird, right? Water is a weird one. You increase the pressure for the same temperature. If you're here, let's say you're at -2. If you're at -2 and at 100, we know that water is ice, right? It's ice at this point. If you increase the pressure at -2, water becomes a liquid. Right? You see that last video. Why is that? It's because water is actually the most dense. It's around 4 degrees Celsius. Water actually gets more compact. It's the most compact in its liquid form. That's the answer. So it's the most compact in its liquid form. Whereas most things are most compact in their solid form. And why is that? Why is water most compact in its liquid form? Because of the hydrogen, because of the structure. Water interacts better with itself as a liquid, right? Being the molecules being able to move around. Water interacts better with itself than when it becomes a solid. Okay, it wants to be closer with itself, and since it wants to be closer with itself, there's less space in between, right? There's not much space here. This is a small distance between this molecule and this molecule. This is a small difference. So because of that, water actually becomes more dense. So when you press it in, it actually becomes a liquid, because when you press it in, the molecules move closer together, but water is actually the most dense as a liquid. So that's why this is an odd one. For other ones, it doesn't do that. Okay, and it's about this hydrogen bonding. That's another reason why, like I said, we give this interaction a special name, and that's because it's so different. You have polar interactions, right? But it's so different from just a normal polar interaction. Well, not so different. It's the same thing, but it's even more than just another polar interaction. This hydrogen to oxygen is such a. But you can also have hydrogen to other things. Okay, not just oxygen, but it's it's a stronger interaction that they give it its special name. So when we have water, right, and delete this, boom, boom, boom. So when we have water, right, let me draw back the game. We have a water molecule. This water molecule is polar, okay? It's polar. So we define polar/charged molecule as A, right? So really, for this structure, we can just draw this structure as A. Now this isn't necessarily a science thing. This is just to simplify, so I don't have to draw this structure every time. I'm just going to use this to show how things work very easily. So you see this interaction, right? Boom. So polar likes to interact with polar for this reason. You have this difference of negative to positive, and then you have the same molecule, right? The same molecule. If you have one molecule only, you have the same molecule, and this molecule acts the same way, right? It's the same molecule. So you also have this negative to positive, and then that means that the positive of the other molecule, the same molecule but just another one, right? 1, 2. This molecule does this thing, negative to positive. This molecule also does this thing, negative to positive. And then the positive of this one goes with the negative of this one, right? That's polar interaction, but when we have hydrogen, we give it the special name. Right? So let's say something else. Let's say you have this. This is pentane. Okay, this is pentane. You have this. How does this interact? Well, this is not polar. There's no. It's the same thing, right? This is the notation. I'm assuming you know this notation. Carbon to carbon to carbon, and this is saturated with hydrogen. That means that all the available bonding sites have a hydrogen on them. All of the extra electrons on the carbons are interacting with the hydrogen. Hydrogen bonding, because hydrogen bonding is between molecules, not within molecules. Okay. That being said, you could have a molecule that has, like on one end, I'm not drawing a full structure, but on one end it would have hydrogen bonding, and if it's a really long molecule, it might have on the other end another hydrogen bonding, and based on the structure, you could have hydrogen bonding within the molecule. That could be possible, but that's not what I'm talking about. I'm just talking about when you have carbon to a hydrogen. That's not hydrogen bonding. Okay, hydrogen bonding has to be a weaker interaction between molecules, or in that extra case, between molecules. And they give it the specific name. Okay? So we have this right here. We clearly don't have any polar, right? There's no difference here. It's all the same molecule. Because it's all the same molecule, you have the same amount. Nothing is pulling electrons more than something else because they're all pulling the same, right? So then how can they interact? Well, they still can, and this one's actually a bit more complicated, but basically on these carbons, right, you have the electrons orbiting around the carbons. I'm not going to go into electron orbiting very much in this video, or maybe another video, but you have it orbiting around the carbons. While the electrons are orbiting, you can see they're at a different point in space when they're orbiting, which means at a certain point in space, a certain time in space, the electrons are at one part. So if it's orbiting here, right, the electrons are at one part of the carbon more than the other. Okay, so this is just the orbiting path. It doesn't mean the electrons at all this at once. This is the orbiting path of the electron. Let's say the electron's here at one point in time. If it's here at one point in time, there's slightly more negative energy, right? Slightly more electron density over here, right, than over here. So the same kind of idea with the polar, except the difference is between this is that the polar is constant. It's always there. So it's a much stronger force because it's always there. Whereas with this, you end up with the electron is temporarily here, which means that temporarily there's slightly more positive over here. Right? There's slightly less electrons over here, and slightly more over here. And then if you have another molecule, I'll draw out the following. Another molecule. Remember, these are saturated, it's not drawing the hydrogens. Another molecule that's also orbiting. The electron's also orbiting. And then it's here, the electron is here in the orbiting path. At the same time, you end up with this interaction. See that? This is called a London force. Okay. And it's actually very strong. Not individually when you just have this. This isn't that strong. But if you have thousands or millions of these forces happening at once, they can be very strong. And that's actually how, I believe, that's how a gecko walks on walls. It's with this London force. Yeah, so that is what geckos use. It's because the gecko has so many, there's so many of these. The way how the gecko structure is, there's like the little, I don't know if they're not hairs, I don't believe, but they're little things. And each one of these are doing this force. So there's so many that they can stick to a wall. So this can be strong, but it's just when you have these molecules together here like this, it's not that strong. But it's strong enough to where at the pressure we're at, this interaction is strong enough to where you actually can make liquids. You can make liquids of various molecules with enough pressure. You can have these interactions such that the molecules, the chemicals want to stay together. Enough of an interaction for that. So that's how these non-polar ones will stick together. Okay, it's the same thing. Weak interaction. I still leave the things. So you see A and B, right? So that's easy of why they're going together. So let's say, in what cases can we have A interacting with B? There's a few ways to do that. The first one is sometimes you can have a molecule I'm not showing how much stuff is in between, but it's long enough such that I wouldn't define the one molecule as being either polar or non-polar. I'll define it that one end is polar, is what I'm showing right now, and one end is non-polar. That's how long this is, okay, such that we can say that one end is polar, one end is non-polar. If you have that, right, that molecule, it's A and B, and you were to interact it with another same molecule of A and B, then what you can do is that these can interact very well, and you can have A, right? I just draw A interacting with A. And B interacting with B. So you can have these large molecules. Why is that significant? Well, if you know what a phospholipid is, they're organic molecules, and they have this structure. They call it, like, they have a polar head. They have not a polar head. I'm not gonna get into biology. They have a polar end, right? And then they have a non-polar end. I think in biology they call it hydrophilic, which just means water-loving. And it's water-loving because it's polar, so it interacts with water, which I showed earlier, the structure, right? Oxygen to hydrogen. I don't think I have to show the whole thing. With the partial charges, right? So it's also polar. So because of that, it interacts with water. Okay? A to A. So for instance, in this doesn't necessarily mean all of the A's are the same molecule. They could be different molecules. What matters is that they're polar. Okay? So A to B and A to B. And then you can have, if you have different ends, you can have interactions. This is significant because, like I said, you have the biology of the hydrophilic head and hydrophobic tail. And because of that, it helps to form different structures. So I notice often you have A, and then it goes to B in here, right? And you form this structure. A bunch of those structures, where it's A to B. The reason why it does it is this. It's because you have the interactions between A, you have the interactions between B, and then the A likes being with the other polar molecule, and the B doesn't. Okay, so this is important. So this relates to everything I'm doing, because when you have a molecule by itself, you have A to A, right? Um, with the interactions, that causes there to be certain properties, right? So you have, like I said, with water, right? You have water interacting with water. Because of that, you have the diagram, right? At different pressures and temperatures, you end up with what the molecule existing as a gas, the molecule existing as a liquid, and the molecule existing as a solid. And for a different molecule, it could be polar or nonpolar, you'll have different pressure and temperatures that exist as a gas, liquid, and solid. And that's because of the different interactions between the molecules, either between A or between B. Or you can have some molecules that are both A and B, and that causes different interactions because of what the molecules are actually made of. So because of the different molecules, you have different molecules. They're made of different things. You end up with different interactions between themselves, and this causes different pressures and temperatures that exist as a gas or a liquid or a solid. Yeah. So then, if you were to have A and B, and then you were to mix them together, right? Well, A and B don't mix. That doesn't happen. So because A and B don't mix, right? Polar and nonpolar, they don't mix. You have the polar trying to interact with polar, right? And you have the London interacting with London, but these won't mix much because and you can also have, there's obviously, and you can have London forces between A and B. That can also happen. It's just that the polar forces between A and A are so much stronger that A really has very little business to interact with B. And if it does, it's not as strong, right? So for that reason, A is going to be with A. And then since A is with A, B is going to be with B. B will interact London forces with B. Okay, so the A is much stronger with the A. I already explained that. So here we go. We have A with A, right? And then B. Well, I should draw it like this always. So because of that, you end up with two phases. 1, 2. You can have a cup with water, right? A. And if I were to put in something that was like this, let's say, you'd end up with, if you added a small amount, you'd end up with a pool of it. And depending on the density of it, you know, if how heavy it is, it would either be floating on the top or at the bottom. This molecule is hexane. I don't know what the density. I think the density of hexane is less than water, so I think it would float. But I'd have to check that. So that's basically what happens, right? So this is significant. You remember in the last video I was talking about, the properties, but I also said when you mix two things, the points at which the liquid evaporates, not evaporates, but becomes a gas, liquid, or solid. And each one, like the point of, let's say if we mix these two, the point at which water becomes a gas, liquid, how much that would occur for these two, because they obviously don't interact much, so I don't know how much changes there would be to individual. But for different molecules, the differences at which the molecules become a gas, liquid, or solid at the different pressures and temperatures. That's why it's important to know how things interact, obviously. And I've gone over the three main ones here, which are polar forces, like I've said, hydrogen bonding is polar forces for hydrogen, and it gives it a special name, and its forces, right, which is called the van der Waals interactions. So I've gone over those. And I've gone over these, and I've gone over why it's important. You have different things, and why there's different. You can see different parts in liquids, and what that actually means for the molecules. How the points at which they are gas, liquid, or solid at the different pressures and temperatures changes when you mix them versus when they're by themselves, when they're individual molecules. Okay, so that's pretty much it for today. I can add one more part. It's an interesting part. So going along with, and I'm going to do my next video. My next video is going to be on the actual difference of when things become liquid or gas at different pressures and temperatures when you mix two molecules together. Okay, and yeah, so that's right. So one more thing is, let's say you have A and B. Okay, A and B, molecule, right? Molecule that's, or a certain bunch of molecules together that are polar. Okay, and B, a bunch of molecules together that are nonpolar. You can actually mix these together by adding in, because these don't mix, right? You end up with a pool of B in A, or depending on how much A and B are, right? You could have, if you have a lot more B than A, you'll have a pool of A and B, right? I'm just defining a pool as whatever is the smaller one, right? So it doesn't really matter. You could have a bunch of B, and then you can put a little bit of water in there, and then you'll end up with water floating within the B. Okay? Because the water wants to, yeah. It does also have something, I'm going to leave that. That's A to B, and this is long enough to assume that A is polar part and B is nonpolar. Okay? You have a molecule. If you do this, then obviously, and if you were to add this to this, right, where you have A and B, and they're interacting only with themselves, right? Maybe small interaction of London force, but like I said, A wants to be with A, and it's that the polar force is much stronger, so A is going to be with A, and then B is going to be with B, right? You're going to have, if you add this, then what you can have is you can have A interacting with the A of this, which then is connected and is separate, and then this B can interact with the B of this, which connects with A, well, not a full bond, confuse you, which has an interaction with A, which then has another interaction, let's say with A, then goes to B, which this interacts with B, and then this interacts with B. See that? So you can add in this thing to two things, one that is polar, one that is non-polar, and they don't want to interact strongly with each other. They don't want to interact with each other in a good way. And then you can have them interact with each other by interacting with this one thing that has both polar and non-polar parts, and then interact, and that now the whole thing can interact with each other. And so this, and then in the solution, it will in the liquids, it will look like one liquid when you do this. So this thing that does this is called a surfactant, and its job is literally just this: to connect two things that aren't mixing, two things that don't want to interact with each other. You add this, and then they interact with each other. well, they don't interact with each other, but then you end up with one liquid, one liquid, where everything connects together. But A still doesn't connect with B. A only connects with A. But these molecules are all linked together. I should say they're all interacting. I think that's pretty much it. And this is how people make things. For instance, like if you were going to make, let's say you make a hollandaise sauce, right? The water, right? The water-based substances. So this is just, water that's part of butter, or you have water that's part of like lemon juice, or you can have whatever other water-based things. If you put another juice in there, whatever water-based things you put in the hollandaise, another fruit juice. This is polar, and then you have the fat, right? The fat of butter. So when you melt the butter and you put these together, right? They don't really want to mix. You might say, why does butter mix then when it's already made? It's because they make A and B be able to coexist in one consistent thing. I'm not going to get into why that is later, because it's not as simple as just mixing things. I mean, it's very similar to this, but it's not the exact same. So, but when you melt the butter, right, they don't mix anymore. So you have, because butter is water and oil. It's not just water and fat. I won't say oil. Water and fat. Because butter is water and fat. So those mix in another way. When you melt them, those separate. Okay, and you melt them to make a hollandaise. So you have the water base and you have the fat base, and these won't mix the way it is. In order to mix them, you have to add something. You add eggs, and the reason why you add eggs is because, well, eggs taste great. That's why. But there's also a surfactant. This thing. There's also this thing in eggs. It's called lecithin, or I don't know how to say it. Let me write it out. Lecithin. It's written like this. Okay, and so you have A and B. So this does exactly what I showed earlier. It connects the A with the A, and it connects the B with the B. And you have to you have to add enough energy, though. You have to add enough energy to actually, what you're doing is you're getting this A and B, you're mixing it around such that the A can actually connect with the A, and then the B can connect with the B. So that's what you're doing when you're mixing a hollandaise. You're trying to get the A to connect of lecithin, you're trying to get the A to connect with the A and the B to connect with the B. And then you make a gorgeous hollandaise. Okay? So that's it. That's what you're doing, and that's why it's happening. So that's mixing two things together. Okay? That's how it goes. When you have two things that don't interact, you can add a surfactant, but you also have two things and they don't interact because one's polar and one's non-polar. Or you can have, these are just interactions between different molecules, what occurs. Two things, you can have them non-interact because one's polar and one's non-polar. And I've talked about all the different interactions you can have. And then why it's significant is because the actual properties of things will change when you have things interacting. Yeah, and that's significant for, right, like I said, the proper pressure and temperature at which point things exist as a gas, liquid, or solid. So the next video, I'm going to actually show, right, how when you interact two different compounds, what actually occurs to the pressure and temperature. And you have that line there, right? where things partially exist as a liquid and gas. I'm going to explain how that changes depending on what you're adding, right? And then, well, how that changes when you have two things, but then also how the amount of the different things changes those properties as well. Changes that data. At what point things exist as a gas, liquid, or solid. Well, not solid. Actually, I'm not going to focus on solids next video, just when things exist as a gas or liquid. Okay, that's everything. So thank you. Thank you for coming.